go to moles, right? Pretty much answer to so many of our how do we start? Go to moles. What can I go to moles of? I go to moles of both my reactants. I'm given a mass of my ferric nitrate, given a volume, a molarity of my sodium sulfide. Anytime we're given quantities of more than one thing, that triggers this whole limiting reactant solving kind of idea. And in order to deal with that, we look at the two reactants separately. We might start with our ferric nitrate. Only I want to go to moles, so grams needs to cancel. And moles need to show up. What do I need in order to fill in numbers here?
Molecular mass.
I need my molecular mass. So I need to look at iron, nitrogen, and oxygen on the periodic table. And look for my total molar mass there. I get 241.88 grams per mole when I do that. I have moles of my ferric nitrate. What do I do next?
Convert to the ones you need to the ones you want.
Convert moles of what I have right now to the moles of what I want. Moles of ferric nitrate need to go away. What am I being asked about? I'm asked about the iron sulfide. Where do I find the numbers for this?
The equation.
My chemical equation. I use the stoichiometry coefficients in my equation to provide my conversion factor. What's going to go in my numerator? A 1. Where did that 1 come from? That's in front of the Fe2S3. What goes in my denominator?
2.
That's where my 2 is going to show up. So this will tell me the moles of the iron sulfide that I could possibly make. In our limiting reactant problems, we can save a little bit of time, a step in calculations. If we hit equals here, that tells us that if we've got 0.691 grams of our ferric nitrate and all the sodium sulfide we could possibly use, that's how much of our product we can make, yes? Once we've gotten this far with our first reactant, we switch our attention to the other reactants. I still need to go to moles, but I don't have grams.
So you have to convert.
Molarity.
I have molarity, and what does molarity tell me?
Moles per liter.
Moles per liter. When I have solutions, molarity is typically going to function with the same, or it's going to have the same function as my molar mass. I've got 36.1 milliliters of this solution. Do I need to do anything with that 36.1, or can I use it?
Convert it to
Per liter.
I've got to go to liters. Molarity is moles per liter. I get to liters by dividing by 1,000. Liters need to go away. Moles of sodium sulfide need to show up. What number goes in my numerator?
Oh, 0.14.
That's my 0.143. 0.143 M, 0.143 moles per liter. I have moles of sodium sulfide. What do I do next?
Mole.
I look at my mole to mole conversion. Change the conversation from the sodium sulfide to the iron sulfide. What goes in my numerator?
1 mole.
Still a 1. What's in my denominator?
3 moles.
3. So whatever is with the chemical stays with it in the conversion factor. That'll give me moles of my product. Once again, I'm going to hit equals.
And for the number of moles, do we always put it like this, or is it okay if we put it in scientific notation?
Using scientific notation is always an option. If it is convenient, you are welcome to use it. If it's helpful, you're welcome to use it. If you want to write out the number, you're welcome to do that. So this number says I could make 0.00171 moles of iron sulfide if I've got this much sodium sulfide and lots and lots and lots and lots of my ferric nitrate. I now have 2 values for how much iron sulfide I can make. What do I do with those?
Pick which one's the limiting reactant.
I think about which one is the limiting reactant and which one then is my limiting reactant here.
First.
The ferric nitrate.
Yep.
Why is that my limiting reactant?
It makes less product.
Makes less product. I will run out of this, and that will stop my reaction. I will have sodium sulfide left over. Once I've picked my limiting reactant, I can come back here and do the last step. Answer the question, convert to the units I was asked for. What did the problem want?
Mass.
Determine the mass. Moles have to cancel, grams have to show up. There's my grams per mole again. So I'll need my molar mass. That's not right. That's right.
Oh, right.
Final answer to our question is that we could make 0.297 grams of our iron 3 sulfide. Does that process make sense? So we did our stoichiometry problem twice, once for each reactant. We picked the one that that could make the least amount, and that's what we use to give our final answer. When we deal with limiting reactant problems, there are a variety of questions that can be asked. And if you've looked ahead at your calculations for the limiting reactant lab, we've got some hints for what other kinds of questions get asked when we've got information about more than one piece. One of the questions we might be asked, how much of our excess reactant, how much of that sodium sulfide was used in the reaction? How can we figure that out?
Take the original mass.
We can take the original mass of what?
Sodium.
We can take the original mass of our ferric nitrate, and we did the same kind of calculation, but we change what we do here, right? We start our problem the same way. If we're going to run out of this, we think about how much of my sodium sulfide would I need in order to consume all of it. As always, I go to moles. Then I think about go from moles of what I have to moles of what I'm interested in. This time it's the sodium sulfide. We go back to our reaction for our stoichiometry. So we can use that to figure out how many moles of our sodium sulfide was used. Does that make sense? Everybody still with me that far? I will take crickets as a yes.
I have a question.
Mm-hmm.
When you say how much NH2S was used, does that assume moles? Or does that, I mean, that could be mass too, right?
If somebody doesn't specify a unit, we're left to make a decision on what is convenient.
Okay. The
In this
quickest.
case, moles probably makes a little bit more sense than mass because we didn't start by talking about mass of our sodium sulfide.
Okay.
Other questions? Next game we typically play in our limiting reactant problems then is to ask how much of our how much of our excess reactant was left over. So in this case, how many moles of sodium sulfide do we have left over at the end of the reaction?
We'd subtract it from
The original.
this one.
Subtract it from this one.
That's the
If we
original.
look at our
versus-
units, this is moles of iron sulfide.
Oh,
If my units don't match, I don't want to necessarily do that subtraction. But yeah, I want to subtract, but what do I want to subtract this from? The total sodium sulfide that I started with. What was in my original solution? How much sodium sulfide did we start with? That's this piece, right? How many moles of sodium sulfide? It's our volume times our molarity. We started with 0.005163 moles of our sodium sulfide. At the beginning of the reaction, we used this many moles. So to find out what's left over, we subtract. And so we should get 0.008778 moles of our sodium sulfide left over. Questions about that? These are all common kinds of questions that we see associated with our limiting reactant problems. How much product could we make? How much of that excess reactant was used? How much was left over? As we look at this series of questions and the solution, our page starts to look like wall O numbers. It becomes important to make sure that you understand what your numbers are telling you. Don't just write a number down, but think about, what have I just figured out and how does it relate to the real world? It's one of the reasons that I try and be detailed in my units, is so that I can keep straight, where am I in the problem? What have I figured out? How can I use that to take my next step? Questions about our stoichiometry variations?
In problems like this, will we be given the chemical reaction, the formula?
For now, yes.
Okay.
Up through chapter 3, we have to be given the chemical equation. We may have to balance it, but we'll at least be told what's going together, what products do they make. In chapter 4, which we'll be starting in a little while, we make the jump to let's start thinking about how do we predict our products. And so, at some point, we do get to play mad scientist. What do I get when I mix?
So assuming if it's already written out, unless it tells you if it's already balanced, then don't worry about it, right?
I would I don't trust anything.
If it is always smart to double check. If it doesn't say, based on the following unbalanced equation, it is probably balanced. But it is always smart to just go through and say, okay, yes, it was indeed balanced, and I can move on with my life. We need to come back and take a little bit more of a detailed look at a couple of ideas that we've brushed past in lecture, talked a little bit about in lab. We need to make sure that they are firm and secure. So we're going to go back and we're talking about composition of molecules. We've started talking about mole ratios. We did the whole copper chloride lab where we looked at mole ratios giving us our subscripts. That's a subset of how we talk about composition of molecules. Often we'll hear people talk about mass percent, percent by mass, percent composition. Those all refer to this same kind idea? Anytime we talk about percentages, we're talking about part divided by the whole. When we talk about mass percent, we're talking about the mass of the part we're interested in, so the mass of a particular element in the compound, divided by the mass of the whole thing. For example, we could look at finding the percent composition of sodium nitrate. When we see a problem like this, what they're asking us to do is find out what percentage of our sodium nitrate is sodium, what percent is nitrogen, what percent is oxygen. There are really three pieces to this problem. Take the elements one at a time. We think about sodium. Now we need masses, but our problem doesn't give us a mass. Fairly common proposition that when somebody doesn't give us an amount of a chemical, we get to pretend that we have however much would be convenient for us to have. So we think about, if I wanted to do this problem, what would be a useful amount to have? And as usual, what is probably a useful thing to think about?
The mass of one molecule.
Well, not just the mass of one molecule, but the mass of a mole, right? Because if we've got moles, we've got easy access to grams. So we're going to pretend that we have a mole of our material. If I have 1 mole of sodium nitrate, how many moles of sodium do I have?
1.
1. How much does 1 mole of sodium weigh?
22.
Whatever's on our periodic table, so 22.9. So that's the mass of the part divided by mass of the whole. What's the molar mass of our sodium nitrate? Take a sodium, a nitrogen, and 3 oxygens. We get 85. Multiply it by 100 to turn it to a percentage. And we get 27.05%. Does that make sense?
So, percent composition is all about mass and it has nothing to do with the number of molecules in it. Because I was...
It depends upon how the question is phrased.
Okay.
If we get a question, determine the percent composition of this, this is what we focus on, and our default is mass percent.
Okay.
We could talk about, I have a mixture. What's the percent composition of the mixture? And that could shift our perspective, our choices a little bit,
Okay.
but it's still going to be the idea of part divided by whole.
Okay. So, I'm glad we did this today because I didn't realize that it assumed mass every time. There was a problem, like the first problem of the chapter 3 homework, where it shows the structure of cysteine.
Right.
So that has to do with mass, correct?
Yes.
Got it.
Yes.
Okay.
We do the same thing for our nitrogen. What's the mass of a nitrogen? Periodic table says it's 14.01 grams. Mass of our sodium nitrate is going to be consistent. We should get 16.48%. Oxygen. Periodic table says oxygen is 16 grams. What else do I have to pay attention to here, though?
The 3.
The 3. My formula says that I have 3 oxygens. I have to make sure that I remember to include that 3. That is probably the most common mistake in these kinds of problems. We either forget to use that subscript or we don't use it correctly. We miscount our atoms. And we get 56.47% from that. We have a built-in error check here. If I add those 3 percentages together, what should I get? I should get 100. Sometimes you might be a little bit off. You might be getting 99.98 or 99.99 or 100.01, kind of a little bit off. You can see that because of rounding error, that's okay. But if you start getting 95% or 85%, you've clearly done something wrong, probably forgotten something. Does our mass percentage make sense? Relatively easy game, but unfortunately it is rare for people to come to us as chemists and say, I have sodium nitrate, can you tell me the percent composition? They don't really need us for that. We tend to get the question asked in reverse. we are much more likely to see questions asked like this. What is the formula of a compound if we know that it's 46.36% tungsten and 53.64% chlorine? Finding percentages of elements in a compound is fairly easy. That's called elemental analysis. That's a standard instrument that we have in chem labs. And so we can take random unknown stuff. You've probably seen this kind of process alluded to if you've watched any of the current crop of crime dramas. Mystery stuff comes in and Abby trots it off to major mass spec and then comes back and says, here's what it is. This is that kind of process. So we need to work this backwards. We're starting here. We need to end up here. But we've got a wee bit of a problem in that we don't know that number. What would we like to know? What is always useful to us?
Moles.
Moles. And if we're going to find moles, what do we probably need? Mass. Once again, we haven't been given a mass. So we get to pick a mass that would be convenient to us. What might be a convenient mass to pretend that we have available?
1 gram.
1 gram, or even easier, 100. Let's pretend that we have 100 grams. Why is 100 grams really convenient for us to talk about here?
Because you can use the percentages as the masses.
I can use my percentages for masses. If I have 100 grams and 46.36% of it, my mass is tungsten. Then I know I have 46.36 grams of tungsten. And how much chlorine do I have?
53.64 grams.
Now I have masses. Now I can think about, let's go to moles. Now I know how many moles of each thing I would have in 100 grams. In principle, I could think about writing my chemical formula from this. W.252 Cl 1.513. But we're really not all that keen on decimals in our subscripts. So how do we turn these into whole numbers?
By the 1, 3?
We have to divide by the smallest moles.
Divide by the
first.
smallest.
Oh, and then.
Yeah.
Okay.
Now at this point, this problem probably starts to look kind of familiar. Where did we play this game before?
Copper chloride.
At copper chloride lab. Once we have moles of material in our compound, we go for that mole ratio. Divide by the smallest. a 1 and I get a 6. What does that tell me?
1.
Mole of tungsten and 6 moles of Cl.
1 mole of tungsten and 6 moles of Cl, so those become
WCl6.
my subscripts. Does that idea make sense? Dana's nodding her head. She's clearly still with me. Anybody else still with me? All right, I got a couple. Look at a similar problem. Talk about the stress hormone, cortisol. What's its formula? It's 69.58% carbon, 8.34% hydrogen, and 22.07% oxygen. Where do we start with this?
100 grams.
We pretend we have 100 grams. If we've got 100 grams, how much carbon do we have?
69.5 grams.
We get 69.58 grams of carbon. We get 8.34 grams of hydrogen, and we get 22.07 grams of oxygen. What do we do once we have masses? Go to moles. I have moles. What's next?
Divide by the smallest number.
5 by the smallest number. divide everything by 1.38. 1.38 divided by itself gives us a nice clean 1. 8.27 divided by 1.38 gives us a 5.99. What are we going to do with a 5.99? That's close enough to 6. However, when we look at our carbon, we get a 4.20. We have to be careful in our rounding in these problems. If we are within about 0.1, then we're good enough to round. But if you're beyond 0.1 and you round, you're probably making a mistake in this. Instead, we need to look at this and we need to think about what could I multiply this by that would give me a whole number. Let's get rid of that decimal. What would be a good choice to multiply this by that would give me a round number?
5.
And multiply by 5. If I multiply that by 5, I get 21. If I multiply this by 5, what do I have to do with my other two?
Multiply by 5.
Also multiply by 5. Now I have whole numbers. Now I can look at writing my empirical formula. What's the formula for this?
C21, H30, O5.
And that's our ta-da moment for the problem. Do those make sense? There's a phrase in these problems that I've managed to get away with not defining yet. What phrase, what word do we not really have a definition for? Both of these have mentioned the empirical formula of the compound. When we talk about the empirical formula for a compound, we're talking about the most reduced version of that. For example, if we look at dinitrogen tetroxide, it's a real compound with the formula N2O4. But what's its empirical formula?
NO2.
NO2. We look at the two subscripts and we look, are there any common factors that we can pull out of all of our subscripts there? benzene has the formula C6H6. What would the empirical formula of benzene be?
CH.
CH. Butane is C4H10. What's its empirical formula?
C2H5.
But how would you able to tell if this compound is nitride or N2 or 4?
Okay, here's the challenge. These problems are only able to give us the empirical formula. What we have here, we have no way to get all the way to the molecular formula to know that, to know whether this is the whole formula or if there's some multiplier. Maybe this is W2Cl12. Maybe this is C42H60O10 kind of thing. If we want to know that we're dealing with the molecular formula as opposed to the empirical formula, we need a little bit more. If we look at this problem, how is it different from our other two examples?
Molar mass is
They give us the molar mass, and they ask for molecular formula. In order to make the jump from here to here, we need access to this piece of information. This problem starts the same way as our other examples. We pick a convenient mass. pick 100 grams, our percentages become masses. We then go to moles. Once we've got moles, we get to think about mole ratio. So we should get a 1, a 3, and a 3 out of that. And what does that tell us? Our empirical formula is COC3O3. So far, it's no different than what we've worked with before. We're here. We now need to work on figuring out how do we figure out the multiplier that gets us back to our molecular formula.
Find the molar mass.
Find the molar mass of
And the empirical formula.
our empirical formula. Since we're dealing with the empirical formula, we typically call this the empirical mass so that we don't confuse it with the molar mass, the mass of the whole thing. But it's found the same way. I took 1 cobalt, 3 carbons, 3 oxygens, and I get 142.96 grams per mole. How is that helpful?
And
I can
find the
divide.
multiple.
My molecular formula is some multiple of my empirical formula. That means that my molecular mass is the same multiple as my empirical mass, right? Because I'm going to get the same kind of proportion out of this. So here's the key to advancing in this problem. Take the molar mass we're given, divide it by the empirical mass, and that gets me my multiplying factor. If I multiply my empirical mass by 4, I get my molar mass. That means if I multiply my empirical formula by 4, I get my molecular formula. compound would be CO4, C12, O12. Does that make sense? Questions about that? Chapter 3's been a big chapter for us. We've talked a lot about chemical reactions, how we represent chemical changes, and we've talked a lot about the calculations that can be associated with them. We've looked at stoichiometry and all of its variations. We've also looked at how we use moles in a variety of ways, including mole ratios that get us through our empirical formulas. Questions about any of our chapter 3 material? And at long last, we get to leave chapter 3 behind. We can put a due date on our chapter 3 homework. It's due 2 weeks from today. Why is it not due a week from today?
Because it's very, very long.
Well, A, because it's very, very long, but also why?
Spring break.
Spring break. Hopefully all of you guys are going to be off somewhere interesting and virus-free. But that wraps up chapter 3 for us. I think that's a good spot for a break. Let's come back in.